Yeah, I'm Till. I'm working at Vereka, and my colleague Guowei works at Alibaba, and we both are working on Flink's one-time engine. And today we want to tell you a little bit about what kind of improvements we added over the past month to improve Flink's batch execution. To begin with, I want to quickly remind you that batch processing can be seen as a special case of stream processing. The only difference is that instead of processing an unbounded, potentially infinite stream, it's a bounded stream. So at some point you've read the file, for example. That's also the motivation why the Flink project tries to unify batch and stream processing under one roof, having one single API and one time to do both. However, this is only half of the truth. The other half is that the property of boundedness can actually be exploited to execute batch jobs or bounded jobs more efficiently. And that's what we want to look into during this talk. All right, in order to see the differences between Flink executing a streaming job and a batch job, let's take a look at how Flink executes these two types of jobs from a very high-level perspective. So when you want a Flink streaming job, what you do, you specify your job graph, you submit it. The first thing which happens is that Flink will bring up the whole topology. So all operators need to be running from the start on to produce results. We have some sources here and there which read from the input streams. And as the data arrives, we need some kind of mechanism to tell us that up to a certain point the data is complete and we can actually start producing some results. This is where the watermarks come into play, which tell us that up to a certain point you won't see any events which happened before this point. And once you see this watermark, Flink starts producing results, potentially incremental results, which are refined over time as you see more and more data and the time progresses. And this goes on for potentially an infinite amount of time. In contrast to that, when we execute a batch job, the first thing is that we don't have to bring up all operators from the very beginning. So it's usually sufficient to start with the sources. Since all the data is usually available when you start the batch job, these sources can read the input data in an arbitrary order. Once they have read the whole input, one can conceptually think that there's watermark, which initially was initialized with 0, jumping to the max value, because no more data will arrive after you've read your file, for example. That's basically also the end of what the sources do. So after they've read the input, they generated the results, which are used by here in our case, by the second stage. Second stage applies some more transformations on the data, giving it to the third stage, which is scheduled after the second one has finished. And once this stage has completed, the job is done, and you have usually produced your result. That's basically how a batch job is executed on Flink. So to sum this up, what are the differences we've seen? So first of all, in a streaming program, we have the concept of watermarks, which effectively trade off data completeness versus latency. Usually, our job produces incremental results, which are refined over time, and we ingest the data in receive order. And all operators need to be running at the same time. In contrast to that, when running a batch job, there are no watermarks. Well, you see the result once the job has completed. And the data can be read in an arbitrary order, potentially optimized for how you store the data. And it can be executed in stages. All right. How can we actually exploit these differences? So when you write a Flink job and run it, the following things happen. So first of all, one needs to specify the program. Here we use a SQL statement, which you give to the Flink optimizer. The Flink optimizer will first build the job graph consisting of operators. And once you have constructed the job graph, it's given to the scheduler where we use the defaults strategies to execute the job. If we now know that we actually are dealing with bounded streams, the optimizer can be a bit smarter. Instead of using the general purpose continuous operators, it could build the job graph consisting of specialized batch operators. So for example, if you have a join operator, it could choose between a hash-based or a sort-merge-based implementation. And also on the execution side, we can use some different strategies to execute the batch job more efficiently. And that's exactly what this talk is going to focus on. So I want to take a look at how we can run batch jobs better than we do it now, how we better use our available resources, and how we can recover faster from failures. All right, so let's start with the scheduling part. When you submit a batch job or a dataset job, the Flink uses the so-called lazy from sources scheduling strategy. The way the scheduling strategy works is best summed up here. So Flink receives the job graph, it generates the execution graph, and the first thing the strategy does is it will deploy all available sources, which we see here. So in our case, we have a job graph with 3 sources. So the next thing the strategy does is whenever an operator has produced some data, the consumer will be scheduled so that it can consume the results from the producer. In our case, we have 2 join operators, which are, where the one produces the results for the second one. This, however, is not optimal if you take a closer look at the available job graph. So you see that we have 2 join operators, which use a hash-based join implementation because we have a build side and a probe side. And when using a hash-based join operator, what we first need to do, or what the operator does, it consumes the build side to build internally a hash table against which it probes the probe side. So this basically means that as long as the first source hasn't been completed, it's no use of starting the second one because this one would simply idle around because the join operator would only consume from the first source operator. This clearly consumes resources, which you don't need to consume at this point of time, so it's a waste of resources. We could improve the situation by being a bit smarter, by taking the dependencies of the different operators into account. So if we have a join operator with a build and probe side, the dependency would be first complete the build side before you schedule the probe side. So taking the exactly same example again, we would schedule first the first build side, which means scheduling the source number 1 and the join operator. After the source has been finished, we can actually schedule the second source operator, which represents the probe side, and right away also schedule the second join operator, which takes the input from the first join operator as its build side again. And last but not least, we would schedule the third source after the first join operator finished. That would be a kind of optimal scheduling strategy for this specific job graph. So how far are we with this effort? Well, the community is not exactly working on what we could call advanced batch scheduler, but first of all to enable this. So what we do at the moment is to make the scheduler component pluggable so that users can provide their own custom implementations, potentially hand-tailored to or optimized for certain use cases to Flink. Of course, we aim that Flink will be shipped with a default scheduler, which will probably work on pipeline regions, more for that later, which works in most cases. But still, there might be cases where an advanced batch scheduler would work better, or there might be other cases where you would want to have something like a if you're facing a straggler problem, you might want to have a speculative execution scheduler. With this work we're currently doing, making the scheduler pluggable, this will become possible. And if you're interested in this topic, then please follow Flink 10.429. We hope to finish this work, like making the scheduler pluggable, with the next release. All right, so much for the scheduling part. Now let's take at another problem you face when executing batch jobs. So when running a batch job, the batch job usually consists of different stages, where every stage can have different resource requirements. And if you have such a job with heterogeneous resource requirements, you soon face a problem. The problem is that Flink's slot mechanism is static. So once you start a task executor, you basically tell, or you decide how much memory you give it and how many slots the task executor should be started with. And this stays fixed for the whole lifetime of the task executor. So if we were to execute this kind of job, where we have two stages, the first stage requires 10 GB of memory per operator or per task, and the second stage requires 5 GB. And we have two task executors where every task executor has exactly one slot with 10 GB. The first stage would be optimal for the setup. We would use all our resources and could execute it. Once the first stage is completed and we start running the second stage, we still need two slots to run these two tasks, but we see that we only use half of the available resources. So basically, we waste half of it. It would be better if we could place both tasks on the same task executor and release the second one. And that's exactly what we try to do with a feature called fine-grained resource management and dynamic slots. So the idea is that task executor is no longer started with a fixed set of slots, but just with resources it has. These resources, the task executor announces to the resource manager, and the resource manager can then slice off exactly sized slots for the respective slot requests. And this will improve the resource utilization a lot. So how would it look like with this example? So again, when we start the first stage, we actually need both task executors, because both of them only offer 10 GB of memory. So here we would create one slot on task executor number 1 and another slot on task executor 2, and run the first stage. Oh, that was too fast. Sorry. And now when we schedule the second stage, we see that we no longer need the second task executor, because we could split the available memory on the task executor number 1 into two slots, fulfilling the needs of the individual tasks. And this would be enough to run both tasks, and then we can free the second task executor, which other applications running on our Yarn cluster or Mesos or Kubernetes will be thankful for. This whole effort is done under the Flip 56. So if you're interested in that, take a closer look at this. Okay, you've already seen this slide, and you've actually seen this before in the keynote. The reason why I've taken it is I think it describes quite well the kind of reactions Flink's batch failover behavior caused in different Flink versions. So before Flink 1.9, when you were running a batch job, I guess you were really scared of failures, because failures were handled by simply restarting everything. So independent of where you were in your job execution, could have been you're 95% done with your job, a failure occurs, you have to do everything again, because Flink will restart everything. This has significantly improved with Flink 1.9, and now I want to tell you what we did and how it works. All right, so the basic idea of improving Flink's failover behavior or speeding up recoveries is to try to avoid redundant work. This is not surprising, but for quite a while we didn't manage to do it. Before I get into the details, I need to introduce a bit of Flink terminology, the data exchange modes we have in Flink, because they become important for that. So when we build a job graph, Flink can decide how two operators are connected to each other, or how they exchange the data. One mode is called the pipeline mode. The pipeline mode means that that you have a producer and its consumer. They need to be online at the same time, so that the producer can send the data right away to the consumer. This is beneficial for low latency jobs or for streaming in general. And then there's a different data exchange mode, the blocking mode. In the blocking mode, the producer first finishes producing all of its data before the consumer is scheduled. Since, like, if you're processing a real-world case or problem, the data can become quite large. The data is not kept in memory, but written to disk or spilled to disk, basically. And spilling to disk or writing or creating a file with intermediate results is effectively a point to which we can fall back in case of a failover. So the idea is basically, if we have like an operator which failed, that we backtrack to the latest intermediate result from which we can resume. And yeah, maybe let's make this a bit more concrete by taking a look at this example. So assume we have the following setup. We have like 6 operators. These 2 are connected via a pipeline data exchange, these one as well, and both produce in a blocking fashion results for the 3rd pipeline region. Pipeline regions is a connecting component of operators which are exclusively connected by pipeline data exchanges. Okay, how would we execute it? So first we would start the first 2 pipeline regions. They would consume some data from somewhere and produce some results. Once these results are ready, we schedule the 3rd pipeline region, which consumes the intermediate results, which are stored somewhere well, concretely in this case, when using Flink's netty shuffle service on the task managers. If now a fault occurs, Flink will backtrack to the latest available intermediate results, and everything on its path will be restarted. So we will effectively restart this operator, nothing else, because we still have these intermediate results available. And that way, it doesn't happen that we will start the job completely. All right, so much for the how the fine-grained recovery works. What do you have to do as a user to benefit from this feature? Well, you have to do a bit of configuration to use it, because per default, Flink uses pipeline data exchanges. What you need to do, you need to enable that at least the shuffle operations are using a blocking data exchange. And you do this by setting the execution mode on the execution config to batch. Or if you want that all data exchanges, so all connections between operators are using a blocking data exchange, you can set it to batch forced. And last but not least, you need to set the failover strategy to use the new pipeline region failover strategy. So you would configure job manager execution failover strategy to region. And yeah, that's it. That way your dataset jobs would use the fine-grained recovery. If you're interested, again, in this feature, then take a look at flip number 1, the very first flip. It has been completed with Flink 1.9. All right, this brings me to the last thing I want to talk about, which is the shuffle service. So for those of you who don't know what the shuffle service is for, it's the component in Flink responsible for sending data from producers to consumers. And depending on what kind of workload you're running, like a streaming or batch workload, there are different requirements for the shuffle service. So a batch workload usually requires high throughput, where a streaming job is more interested in low latency data exchanges. Luckily, Flink's default shuffle service, which is based on netty, is really good at both things, but it's implemented against a certain set of characteristics. And if it happens to be that you need a different set of characteristics, then it was not possible to work around this up to Flink 1.9. And another problem is that the netty-based shuffle service stores the results in the container of the producing task. This means after the task is finished, we cannot release the containers, the compute resources right away, because the results first need to be consumed by the consumers, which basically locks up resources. The way to solve this problem is that we also made the shuffle service pluggable, so that we can provide optimized implementations of a shuffle service for specific workloads. So for example, we could have a different shuffle service implementation which does shuffling differently. At the moment, the netty implementation uses a hash-based shuffle, which produces many small files, whereas a sort merge-based shuffle would produce fewer files and has other performance characteristics. And we could even provide a shuffle service implementation which stores the data somewhere else, decoupling the intermediate result storage from the compute resources. And that way, we could release these resources much faster. A potential external shuffle service implementation, which my colleagues at Alibaba implemented, is a topic of what Guowei will talk about in a second and give you more details of how it works and what the improvements are. And that's actually where I would like to hand over to my colleague Guowei, who will tell you now more about how these batch improvements are used at Alibaba. Thank you.
Thanks to you for sharing the new batch architecture in Flink. Next, I will introduce how we use the new batch architecture in Alibaba. And I will show two cases. One is about the scheduling. The other is about the shuffle plugin. Currently, Flink has two scheduling strategies. One is the eager scheduling strategy, which is for the streaming job. The other one is lazy from source scheduling strategy, which is for the batch job. The lazy from source scheduling strategy sometimes it works well, but sometimes it does not meet our needs. It represents in two ways. The first is about the resource utilization. The Theo has already explained it. Another is about the performance. Currently, Flink supports two shuffle modes. One is the blocking shuffle. The other one is the pipeline shuffle. In most cases, the pipeline shuffle performance is better than the blocking shuffle. However, most the batch job users prefer to the blocking shuffle. One reason for this is that the lazy from source strategy only considers the input dependency. This means that if the user set the execution mode to the pipeline mode, the job might be a failure owing to the insufficient resources. This also means that the most batch job user cannot take advantage of the benefits of the pipeline shuffle. To solve these two problems, we developed a new new batch job scheduling strategy based on the new Flink batch architecture. The strategy, we called it dynamic group scheduling strategy. The basic idea for resolving scheduling the idle task is that introduction the scheduling hints. And the plugin could use the scheduling hint to schedule the right task at the right time. First, we add some properties. To the transformations, and these properties indicate how the operator read the inputs, for example, the read priority. And we also add some properties which indicates how the operator outputs the record. For example, the operators need to begin to emit the record only after he finished reading its inputs. Secondly, these properties will be converted to the scheduling hint when generating the job graph from the transformations. And currently, we use control edge to represent the scheduling hint, and we now support three scheduling hints: concurrent, sequential, and start on finish. For example, the start on finish means that the target task should be scheduled when the source task is finished. At the runtime, the plugin partitions the job graph to some static groups according to the control edge. The tasks in the group could be work at the same time and does not have any idle tasks. The plugin uses scheduling hints to avoid scheduling the idle tasks. Next, I will do a simple introducing how we make the bad job user to use the pipeline shuffle without worrying about the job failure owing to the insufficient resources. The general idea is the task will use the pipeline shuffle when the resource is enough, and fall back to the blocking shuffle when the resource is not enough. First, when the plugin decides which task to schedule, it not only considers the dependency is satisfied or not, but it will consider how much resource it could taken. Based on these two factors, this plugin only schedule the tasks whose resource and dependence are both satisfied. We call this task scheduling group because the resource is different at runtime, so the group might be different. So this is why we call this plugin the dynamic group scheduling strategy. In a summary, this plugin uses scheduling hints to avoid scheduling the idle task and considering the resource at runtime when scheduling the tasks to avoiding the job failures owing to the insufficient resources. Okay. After the scheduling, I will introduce the external blocking shuffle service. Why do we need this external blocking shuffle service? There are two reasons. The first reason is about the task manager cannot be released by the resource manager, even if there is no tasks in it. This idle task manager means that the resource of the cluster cannot be fully utilized. And this phenomenon is very common in our production environment because most of our bad job users prefer to use the YAP job mode. The second reason is about there are multiple shuffle services in a same machine, and they are working independently. And they doesn't not have a global view of the I/O system. This means they cannot. This is not the best way to use the capability of the I/O system. To solve these two problems, we developed the external blocking shuffle service based on the pluggable shuffle service architecture. The general idea to resolving the resource utilization is that we launch auxiliary service for the transmission of the shuffle date in every node manager, and the right part of the shuffle service will respond for write the date to the disks. And when task is finished, the shuffle service is notified. Then the shuffle service could respond for the read requests. Since the task manager does not respond for the data transmission, it could be released in time, and this resource could be used by another job. Actually, we not only migrate the shuffle service, default shuffle service from task manager to the node manager, but also we do some improvements for the blocking shuffle service. Next, I will introduce some optimization we have already done in the external blocking shuffle service. The default shuffle service use high shuffle mode. The pros of the high shuffle mode is that it's very fast because there is no sorting at all. There is no extra memory overhead, and there is no overhead of the extra I/O operation because the data is only write once and read once. But the cons for the high shuffle is that it will create a great amount of the files, and most of the I/O operation are random ways, which is much slower than the sequential ones. So we introduced the short merge shuffle, and the pros of the short merge shuffle is clear that it will generate much less file than the high shuffle, and the I/O operations are sequential ones. The cons for the external shuffle service is that there is no obviously advantage if user use some SSD drivers, and if the job's mode is very smaller, and it might be a little slower than the high shuffle mode. This means that different shuffle modes are required by at a different time. So we kept both the high shuffle mode and the short merge mode in the external blocking shuffle service. Another optimization is about the disk school, and the write disk are selected in a random way in the default shuffle service, and this will lead to disk screw. And we found there in our production environment, there are many of the long tail tasks caused by this situation. The write disk is selected according to the all disk load in the external blocking shuffle service, and this reduced the most the long tail task caused by disk school. We also do the special optimization for the broadcast partition. We only serialize once and store one copy of the record. The above describes the optimization of the external shuffle service in terms of the writing part. Next, I will introduce optimization we have done about the read part. It's about we convert the random I/O operations to the sequential ones as much as possible. The upstream of the default shuffle service use a FIFO queue to serve the read request. It leads to a lot of random I/O operations. And we use, in the external blocking shuffle service, we introduce a priority queue, and the file with most credit are served first, and this maximizes the readability of the disks. Okay, that's all.
All right, thanks, Guowei. So this is just to wrap it up. So what have you seen today? One thing is that the Flink community works hard on improving the batch experience. So some of the features are already contained in the latest Flink release. Others are being worked on and can be expected with the next releases. So the community is dedicated to further improve there. And this is also, I think, very important for a truly unified stream and batch processing engine. For those of you who wondered whether this cool technology, like this external shuffle service used at Alibaba, will be made available, yes, it will be. The discussion hasn't started yet, but I expect that this happens soon, so that everyone can benefit from this cool piece of technology. So you should check the mailing list and the release announcement for that. All right, thanks a lot for your attention. I think we are a bit over time, but we have a couple of minutes for questions, if you have some. Thanks a lot.
Okay, this is a question for Till. When I hear you speak about the new architecture, I immediately start thinking about like having streaming job with a bootstrap phase, and I would have the bootstrap phase in a blocking fashion, and then switch over to the other one. Will the new architecture support this, or?
No. This won't be part of the first scope we're currently working on. This is, I think, a bit farther in the future. But this is a very valid use case, and many people ask for that. And I think this is, would be great to add soon to Flink.
Thanks for the talk. I have a question about these the forced batch mode. Do you have any idea of like performance costs of that in terms of throughput, latency, storage? So I can imagine if I have to store all my blocking the blocking data at every stage in the pipeline, that if I have maybe 100 gigabytes of input, then it's 200, 300, 400. Do you clear it up or afterwards and stuff like that?
Yes, we do. So maybe that's one part I left out. So whenever you have a pipeline region, so region connected by components, operators connected by pipeline data exchanges. Once this region finishes and completes and has produced its intermediate results, the inputs to those regions will be cleaned up. So you should only keep the intermediate results of one stage at a time. Others will be cleaned up, so it should not add up. What the exact implications are for a job heavily depends on the actual job you're running. Maybe, I don't know, Guowei, do you have some experience what the effects of using blocking data exchanges are compared to using pipelines?
Yes, as far as some benchmark, that there may be some case, maybe three times or 2 times better than the blocking shuffles.
Yeah, so you pay a little price or some costs for having faster failovers.
Hi, I have some questions. Actually, I have 2 questions. One particularly around the external shuffle service and the pressure on the yarn node managers. How big of a cluster have you particularly tested around, and also when you have a large number of files? what we found is that when we have a huge cluster, there's a lot of pressure on the node manager itself. If you use the external shuffle service to have additional things that the node manager has to manage, what's the impact on that? The second question is actually around, in the keynote earlier today, the mention of combining, potentially getting rid of the dataset API into a data stream API to handle batch and streaming. How does this particular improvement then merge back in?
Maybe let me try to answer the second question. Maybe the first question is a good fit for Guowei. All these changes we added to Flink will also be relevant for the future data stream API when running bounded jobs. So yeah, that's just at the moment, you can only benefit from that when using dataset API or using the table API or SQL with the Blink planner, which also sets blocking data exchanges. That's the limitation. Why with the data stream? I mean, you process unbounded streams at the moment, and it uses pipeline exchanges. So these faster recoveries, yeah, you wouldn't gain anything from that because it's not used. But in the future, this will change.
Okay, I repeat your problem. You mean that the scale of the cluster? Yes.
Yeah. So when you have a large cluster with a large number of files, right?
Yes.
The number of data exchanges and requests to the node manager itself are much larger,
yes.
right? It's because you typically have one or two node managers for the whole cluster. So then if you kind of putting the shuffle service onto the node manager itself, what's the impact? And then how far has this been benchmarked before?
Okay, yes. Actually, we are cluster about 1,000. Actually, this, we do some other restriction on the node manager. We limit the connections and the upstreams and the downstreams to avoid the too much overload for the node manager. Also, we do a lot of the load balance between the different node manager. Yes. Okay.
Any more questions? Yeah.
Sometimes I face a problem with batch processing, almost with another frameworks, especially with the small files. I have it for example, to compaction service. Do we have something from Flink to tune that problem of small files?
Of small files resulting from...
So, for example, I am reading a partition of data. It contains 1 million file. It is coming from Kafka because it is real-time data and small files. And if I use the Spark, for example, for that, I spawn very, very big cluster to open all of the sockets and read from each file. And if I didn't have before that stage of using directly that is partition or that is data directly, I have a problem for waiting and long time for just bringing that is data from sources to the processing cluster of a Spark, for example. But if I use the Flink, does it make a change for me for that case or not? The question was not clear.
I think to answer this question, I would need a bit more input on the concrete problem you're solving, but maybe we can take it offline and try to solve it.
Yes, take it offline. I think it's better.
Because there's the coffee break, I guess.
Yes, there's a quick afternoon break, and then next session's coming up. Yeah. Thank you very much.
Thanks a lot for your attention. Thank you.